Hello, Assalamu alaikum. Myself is Dr. Ansari Farzana, Veduzama, Department of Chemistry, J.A.T.rts Science and Commerce College for Women. Welcome all of you. In previous section, we have seen about the component, phase and degree of freedom and also the phase rule. Today we shall discuss about the one component system, for example, water. Knowledge of analytical geometry tell that to locate a point in an area, its x and y coordinate should be known. To locate the point on the line or on curve, it is sufficient to know x and y coordinate. Likewise, to describe the system in an area, the two variables must be specified while describing the system on curve. Only one of the variable is to be specified. Applying the phase rule to one component system, the expression can be written as f is equal to 1 minus p plus 2. That means it is equal to 3 minus p. When only one phase is present in the system, f is equal to 2, and both variable pressure and temperature must be specified for complete description of the system. Such a system occupies an area on the phase diagram. When two phases coexist in a state of equilibrium, f is equal to 1. Thus, either P or is specified to describe the system completely. A curve represents the system at equilibrium on the phase diagram. When three phases coexist in an equilibrium, F is equal to 0 and neither pressure nor temperature is specified on the phase diagram. Such a system at equilibrium is represented by the point. See here, for example, water system. In the present discussion, consider the temperature above minus 20 degrees C and pressure below 2000 atmosphere when three limits. These limits only one solid phase for water is possible, namely ordinary ordinary ice below a temperature of minus 20 degrees C and above 2000 atmosphere pressure. Other modification of ice coexist. The phase diagram for water system is shown in the figure. See your figure. It is divided into three parts. AOC here the water exists only in the ice form, whereas in COD the water exists in a liquid form, whereas in the area AOB it exists in the vapor form. The diagram is divided into three areas. To the left of a curve OC and above the curve OA, that means area AOC, water exists only as ice, whereas in the area COB, water exists in liquid state only. Below the curve, that means in the area AOB, only water vapor exists in the system. In all the three areas, the system is bivariant and both the pressure and temperature must be specified to describe the system completely. There are four curves. Curve AO. AO, that means here curve AO. Curve AO, curve OC, curve OB. Curve AO It is formed by intersection of the area in which water exists only as ice and vapor respectively. The curve represents the water sublimation curve of ice. Along the curve, ice exists in equilibrium with its vapor. Ice has characteristic vapor pressure at different temperature. The system is monovariant and to describe it completely either pressure or temperature must be specified. The curve OB, it is formed by the intersection of area representing the liquid and vapor phase of water. The curve represents the variation of vapor pressure of liquid water with temperature, and along the curve liquid water exists in equilibrium with its vapor. The system is monovariant. The curve extends from O to the critical condition of water at Tc is equal to 374 degrees C and Pc is equal to 220 atmosphere pressure. The line OC. It is formed by the intersection of area representing the solid and liquid phase of water. The curve represents the variation of melting point of ice with pressure. Along the curve, ice exists in a state of equilibrium with liquid water and the system is monovariant. The slope of the line is negative, indicating that the melting point of ice decreases with increase of pressure. Increase of pressure lowers the melting point of ice. According to Le-Chatelier principle, line CO run from point O up to point corresponding to 2000 atmosphere pressure and about minus 20 degrees C. At this point, ordinary ice in equilibrium with water undergoes a transformation into another solid form in equilibrium with the liquid. The dotted curve OD. The dotted curve OD. See a OD. OD. The curve represents the metastable equilibrium between liquid water and its vapor. The curve, therefore, is an extension of the curve BO. Along the curve, liquid phase exists below its melting point without the separation of solid phase. At each temperature, the vapor pressure of liquid is greater than the expected equilibrium pressure for ice, thereby representing the metastable state of the system. The system is monovariant. The triple point, the curve AO, OB, and OC all intersect at a point O. At triple point O, the three phases of water, namely ice, liquid, vapor, coexist in a state of equilibrium. According to phase rule, the system is non-variant, thus the three phases coexist in a state of equilibrium at a definite temperature and pressure. Use of phase diagram. The phase diagram can be used to predict the change of that all that will occur when the pressure is changed at a constant temperature or vice versa. Suppose that we want to go from state X to another state Z of the system at the constant pressure. At X we get only ice in the system as the heat is supplied to the ice at constant pressure. Its temperature will slowly rise till a point Y is reached. Y is the melting point of the ice. The supplied heat will be utilized in melting of the ice, and the temperature of the system remains constant till ice coexists in equilibrium with water. Once the ice melts completely, the system contains only liquid phase of water, then temperature begins to rise. This will continue till water will begins to boil, and again temperature of the system will remain constant till water is in equilibrium with vapor. The supplied heat is utilized in converting water into vapor. Once the conversion is complete, the temperature of the vapor will begin to rise. This continue till a state Z is reached. See here, this curve indicates that the area AOC, ordinary ice, is obtained. The phase that exists is in the region is ordinary ice, and the name and number of degree of freedom F is equal to 2. Area COB, here the liquid water is exist, and again freedom is F is equal to 2. Area below the curve AOB, vapor is exist, freedom is 2, pressure and temperature. The curve AO, in this curve AO, solid is in equilibrium with vapor, therefore degree of freedom is 1. The curve OC, solid is in equilibrium with liquid, therefore the degree of freedom is equal to 1. The curve OB, in the curve OB, liquid is in equilibrium with vapor, therefore degree of freedom is equal to 1. In the same way, the curve OD, metastable equilibrium, liquid is in equilibrium with vapor, is supercooled, therefore degree of freedom is 1. The point 0 or the point O is called triple point. Here the solid is in equilibrium with liquid, is in equilibrium with vapor, and therefore it is independent on the variable, and degree of freedom is equal to 0. Now consider the phase diagram for the carbon dioxide. See here, the curve ABC, area ABC indicate that in this area the solid carbon dioxide is exist, whereas CBD, here in this area the liquid carbon dioxide is exist, whereas in the area ABD gaseous carbon dioxide is exist. The phase diagram, this is the phase diagram of carbon dioxide. Description of area. The phase diagram is divided into 3 areas, as we have seen that to the left of the area BC and above BA. BC and above BA. That means area ABC. This is called the area ABC. Area ABC. Carbon dioxide exists in solid form. To the right of the curve BC, the above curve BD, area CPD, carbon dioxide exists in liquid state only. Below the curve BA and BD, area below ABD, only carbon dioxide vapor exists in the system. There are 3 curves. The curve AB. AB is the sublimation curve along which solid carbon dioxide is in equilibrium with gas, whereas curve BD is the vaporization curve along which liquid carbon dioxide is in equilibrium with gas. The curve BC is the fusion curve along which solid and liquid carbon dioxide are in equilibrium with each other. triple point. B is the triple point at which three phases of carbon dioxide coexist in equilibrium with one another. See here, triple point is nothing but B. B is the triple point. See here. The temperature of the system at this point is minus 57 degrees C, while the pressure is 5.2 atmosphere. A slight variation in temperature or pressure at this point may result in the disappearance of one of the two phases. For example, a slight increase in temperature will result in the disappearance of solid phase and the equilibrium will shift along the curve BD, while a slight decrease in temperature will result in the disappearance of liquid phase and equilibrium will shift along the curve BA, keeping the temperature constant. If the pressure is increased, the gaseous phase will disappear and the equilibrium will shift along the curve BC. Use of the phase diagram. The phase diagram of carbon dioxide is similar to that of water in showing three distinct areas of solid, liquid and gaseous phase. But phase diagram of carbon dioxide differ from water phase diagram in several respects, such as the fusion curve slope away from the pressure axis. This indicates that increase of pressure increases the melting point of the solid carbon dioxide. That means factor dt upon dp of the Clapeyron-Clausius-Clapeyron equation is positive, indicate that a specific volume of liquid carbon dioxide is greater than that of solid carbon dioxide. The solid carbon dioxide can exist in equilibrium with the liquid, that means it can be built only at a very high pressure equal to 5.2 atmosphere. This is unlike to water system in which ice and water can exist in equilibrium even at very low pressure 4.58 mm of Hg. The vapor pressure of solid carbon dioxide, even of the extremely low temperature, is very high and many times higher than that of ice. The significant features of carbon dioxide system is that even at atmospheric pressure, that means 1 atmosphere pressure, carbon dioxide gas can be directly solidifies without appearance of liquid phase merely on cooling to 78 degrees C. For this reason, carbon dioxide is commonly known as dry ice. Thank you for watching.